So I gave you the lists. Okay. Now I'm hoping to get into a chapter 13. Chapter 13 is a little bit big chapter. And but the test will come after chapter 13 is uh, studied. So we're looking into maximum 2 or 3 weeks from now on. You're going to probably see the first test. Okay. So I don't know which date, but it's coming soon. Okay. Let's go ahead and take a look at this. So this is about 30-degree incline.
Are you recording, Professor?
Thank you. Okay. All right. I'm going to close the quiz number 5.
Professor, I'm just submitting the quiz.
Yeah. Okay. So go ahead and do it now. And this guy has a weight, FW. Weight is force. Somebody said something about the force. That's the force right there. And there is the normal force acting, okay, by the wedge onto the block. This is a block. Wedge, okay? And also there is a friction force.
Professor, you're not recording at the moment.
Thank you. I must be having a short memory. Thank you. Okay.
You're good now. Thank you.
So the friction here would be friction coefficient mu times the normal force. Okay. And this block is not going to going up, right? It's going to be traveling downward and with a acceleration of 3 meters per second square. Okay. So I'm going to put that's going to be the X and Y. How's that? Okay. That's going to be the positive directions. So the force is equal to MA along the X directions, and downward is positive. So in this case, the weight will be split into this. So this is 30-degree, and this is also a 30-degree. So this force is W times cosine of 30. This guy is W sine of 30. So this is a components of the W. So checking in here, and this guy is downward direction. That's a positive. W sine of 30 minus this friction force is reacting is equal to mass times acceleration. In this case, acceleration was 3. Okay. What about the motion in the y direction? But however, I do not have acceleration in this direction. So that's going to be equal to 0. And the upward direction, I'm going to call that, that's going to be my positive. So n, normal direction, is positive. And the components of the w in this y minus y direction is w times sine of 30, okay, equal to 0. So this is one equation. This is the two equations there. I'm going to solve for n, which is w times sine of theta, and I'm going to substitute that in right there.
Professor,
Yes.
for the summation of the forces on the x direction, I think you put sine of theta instead of cosine of theta.
Thank you. That's a cosine, isn't it? Thank you. No, let me take it
It's
back.
a sine, yeah.
This is a sine, sorry. So this is where I made a mistake. This is 30, okay? So this is still be the sine, okay? And this guy will be cosine. So W, now the n is W times cosine of 30, and I'm going to substitute that in. So what I am having is W sine of 30 minus mu times W cosine of 30 is equal to mass times acceleration 3, right? Now the mass is basically W divided by gravity times 3. So I can knock this out right there. So if I were to solve for the mu, okay, in this case, then it's going to be sine of 30 minus 3 over g divided by cosine of 30. Okay, so g here is going to be a, what is it, 9.8. Okay, so when you multiply and divide and whatever, then you will have something like this value. So that is the answer. Okay. Now, somebody was asking, hey, is there any other forces? Okay. Force is something like this that you're looking for. Okay. What's the other mass of it? It's m. So things kind of drops out in these cases. So
Well, hold on. Is mu unitless?
mu, let me see. In this case, yeah. Yes.
It's just a coefficient.
Coefficient.
Yeah. Okay, just making sure.
The coefficient of friction. Okay. All right. So that's how you do it. Let me see. Okay, I'm going to close this guy. And I'll have this one open for one more day. Make it visible for you. Okay.
Can you please also remember to submit the videos that recorded already?
I think it's a little bit late. It's a couple of weeks late. I don't know what needs to be done there. So
You just can share with us the link,
say that again.
the link of the Zoom recording. It's just link.
Yeah, I'm gonna probably set that up soon.
Thank you.
Um, okay, I'm going to take a look at the one other problems. Here is the other poll. I think when you go see, elementary school or somewhere, there is a string attached to it. There is the ball right there, and you start to hitting it. And this guy travels in a circular motion. And the cable was measured to be 1.8 meters. And the velocity was measured to be 4 meters per second. And we are going to assume this ball of a mass of 450 gram traveling at the 4 meters per second, fairly constant velocity. Okay. Find theta and tension on the cable. Okay. So let's take a look. So if the ball is over here, you're going to see the velocity. Okay. What is it? Tangential to the path of the ball. In this case, it's a circular motion. Now, if the mass is moving along the curvilinear, moving along the curve, and you should immediately think that there will be an acceleration in the tangential directions, and the acceleration toward the center of the curvature. In this case, the center of the circular path. Now the velocity is constant along the path in tangential direction. So most likely your AT, acceleration in the tangential direction, which is a tangent to the circular, would be equal to 0. But the normal component of the velocity still exists, which is v squared divided by the radius. Now, this radius is not this number. This is the radius of the circle. So once we know, then we should know what the radius is. All right. To attack this problem, you need a free body diagram. Okay. So this is going to be my tension directions. And the weight of the ball acting downward. And this is going to be the direction of the acceleration, which is going to be velocity squared divided by the radius. The radius is somewhere here, right? Okay. Now, first of all, I'm going to take the Newton's equation, force equal to MA, but in this way, it's to the normal directions toward the center of the path or the curvature. And I'm going to use the sign convention. Anything toward the left, the force term shall be positive in that. So the tension in this case has the components in the normal direction. Okay. So this is the theta direction, and that is theta. Okay. So in this case, you have this component is t times the sine of theta. Okay, so I have to be a little bit careful. I goofed just a minute ago, sine and cosine. So this guy has the components t times sine of theta, okay, which is equal to mass times the velocity divided by the radius. The radius is given right there. So that radius is 1.8 times sine of theta. This is theta right there. So this is the R value. So that's going to be 1.8 sine of theta there. That is the equation. Okay. Now, taking the what is it? F equal MA, and I want that to be in this direction. That to be my Y direction. So I'm going to take the anything. What is it? Toward upward. It's going to be a positive. Okay. So in this case, the component of the t along the y direction, okay, would be t times the cosine theta positive, okay, minus w equal to mass times ay. In this case, is 0. Why? Because this is the only acceleration that it can see. There is no acceleration up and down. Okay, so in this case, your t cosine theta has to be equal to weight, which is going to be mg. So solving for t equal to mg divided by cosine theta. So you have two equation with a unknown, two unknown. This theta and the what is it? The other tension. So I can go ahead and substitute that in over there. Then it's going to be a mg cosine of theta, sine of theta equal to mv squared 1.8 sine of theta. Then you can just go ahead and solve for that. So I have two of them, sine square, v square, cosine theta 1.8 g. Okay, now this guy is equal to 1 minus cosine square theta equal to v square cosine theta 1.8 g. So this looks like you can go ahead and put that in a cosine square plus v square cosine theta 1.8 divided by g minus 1 is equal to 0. So this is quadratic equations. So you should be able to find cosine theta, two thetas, okay? And the one that I accept, the value would be 0.64479. Okay? The other value that should not make any sense. So in this case, theta is about 49.9 degrees, about 50 degrees. Okay. So once you get the 50, punch that in here. Okay. And then you should be able to get the tension value. Okay. We know what the mass is, 450 gram, which is 0.45 kilogram. G is 9.8 meter per second square. Theta is about 50 degrees. And if you compute that, it should came out to be somewhere closer to a 6.85 newtons. Okay, so this is how you solve this type of a problem. Okay. Now, we talked about the linear momentum equations in the chapter at the beginning of chapter 2. Okay, I'm going to define the linear momentum to be mv. Okay, and if I take the derivative with respect to time, and this guy is definitely m times dv dt. Okay, time derivative on, right, the velocity is going to be your accelerations. So therefore, time derivative on the L should be equal to m times acceleration, which is a force. Okay, and this is known as a L, which is linear momentum. That is simply mass times the velocity. Okay, so changing, put another, this is basically dot. So changing in linear momentum is equal to force. Okay, the force is in the force is the if there is any time changes on the linear momentum equations. So that's what the baseline is. So if f is 0, that means the dl dt is equal to 0. Only way that this guy is 0 if L is constant. So linear, when you have a constant linear momentum in your system, then there is no net force applied. So here is your mass moving somewhere with a velocity that creates your linear momentum. Now, at certain point, you wanted to know where that mass is, and you wanted to find the r times mass times velocity. And this is known as a angular momentum. So angular momentum is r cross product with a linear momentum. Okay, I'm going to differentiate those. Take the derivatives, not differentiate. And okay, first one is I'm going to put the dot, no changes in the second, and no change. Okay, and then take the time derivative. Maybe I can just go ahead and do it. mv dot. This guy is, by definition, it's a velocity. And this guy, the time changes of the velocity with respect to time is, that's an acceleration. Now, when you take a look at this guy, when you cross with the same vector, that's equal to 0. This guy is what? Mass times acceleration is going to be your force. Okay, this quantity from your static, class, R cross F is known as what? What is this equal to? Does anyone know? That's your moment. The moment is defined position, moment arm, times the force. So your moment is equal to the time change, okay, the rate change of angular momentum of your dynamic system with respect to time. This one, I'm going to call it a H bar dot. Similarly, force is equal to L dot. Okay? If net force, moment, and the force are equal to 0, then this guy will become 0. That means that not the time derivative, angular momentum should be constant. If the force is 0, your linear momentum should be constant. They may not be equal, but different values. Okay, and they, being constants. Okay. We have some, let's say we have Earth, or have some, the satellite, or it could be the Earth moving along the about the sun, right? So we have a force, kind of a gravitational kind of, okay, and it enters through the center, okay. And if you were to take the moment about the other center, there isn't no moment arm, even though there is a force here, force of attraction, and the moment is 0. So in this type of motion, our angular momentum should be constant. Okay. Now note that, again, we're going back to that same step. And this is the position R. And this guy moving here, velocity with a m. Now velocity has a may have two components in a polar coordinate system. Okay, let's say this is V, and this is going to be V cosine of V, and that guy will be V sine of V. Okay. So if you were to take the angular momentum about the this O, so R bar cross M times V sine of V in here. No, hold on a minute. The original definition would be MV. Okay. Now this guy will be break it into V. This would be the components. V cosine of V in the R direction plus V sine of theta in the the transverse directions. But when you cross this thing, this is here to here. So the angle between these two vectors are to E tangential, or the radial direction I'm talking about. This is ER, the radial direction, and this component goes to 0. So what's left is R crossed with V sine of V E theta much. So the dropping the the vector, we only have a R V theta. Okay, so V theta is basically this guy. Okay. Okay, and that there is a mass here. Okay, so from the polar coordinate system, this is designated to be R theta dot. So therefore, H naught is equal to M R square theta dot. Okay, this will be constant. Okay, so those people who are in a aerospace engineer, you're gonna probably take some classes dealing with the astrodynamics, and you probably want to know the fundamentals of this. Okay, we'll probably revisit this a little bit more later. Now we are moving over to a chapter 13. It is about the work and energy. Okay, this is another method to solve dynamic problems. And we know starting from F is equal to MA. Okay. Now, your force is equal to, okay, I'm going to drop the, the vector, okay? It's either going to be Fx, Fy, Fg is equal to Ma. Your mass, is M. This guy is dV dt. Now I'm going to rewrite this with a dr dt. This guy is a velocity. Boy, this looks familiar. And I'm going to put the dr, and I'm going to do that, and integrate over, okay, over position 1 and 2, velocity 1 and 2. And this guy, I'm going to call it as some kind of u going from 1 to 2 equal to, this is going to be 1/2 times mv squared evaluated at the v1 and v2, and that gives me a 1/2 times mv squared minus 1/2 times mv1 squared. And this is known as a kinetic energy. It's defined to be 1/2 times mass times velocity squared. And I'm going to call this a kinetic energy at the 2-second position. This is going to be kinetic energy at the initial or first position. So this is going to be something like this. So this guy is basically has a definition of integration of force times distance. So therefore, this is a kind of a work formulations. So actually, this is the work done by the external forces that introduced in your dynamic problems or systems. And because of the minus, I'm going to push that onto the other side. It's going to be the work done by the external forces is plus T1 is equal to T2. Okay. So before I can jump onto it, let me say something in here. If I put some kind of work into, dynamics, okay, if I, put something into it, it disturbs, your dynamic system. How it is disturbed, there will be a changes in the kinetic energy in your system. Okay, that's how you understand. If there is a changes in your kinetic energy in your dynamic system, that means something must have been done something from somewhere. Okay, you can kind of think it that way, okay, in a layman terms. Okay, more philosophical terms, you may want to refer to that nice, theorems or paragraphs in the textbooks. Okay, so this is an energy equations that you and I want to work with. Now we're going to further investigate what the U goes from 1 to 2, work done by the external force. Here is the weight. I'm going to move this one from here to here. So this would be my position, let's say y1, and that's going to be my position y2, okay? So difference here is y2 minus y1. Okay, so when I move W of the block of the weight W, and actually this guy, the load or the force applied here is moving downward against the direction of that I'm moving. So this is kind of equivalent to the dr, and this is kind of equivalent to the force. Okay. So U was defined to be force times, in this case, okay, but the small, movement will provide the small changes in the, work energy. And this is a dot product, which means the, what is it? The magnitude of force and the magnitude of the the travel distance, and times it's going to be cosine of theta. What is this theta? That's between the force and the dr. Okay, but when you look at here, force is in this direction. Your dr, in this case dy, so that is almost 180 degrees. So I'm going to put that as a 180 degree. So force in this case is the weight. dr is dy, and the cosine 180 is minus. So here is du is equal to w times dy. So this is the work done by trying to raise from the from y1 to y2. I'm trying to raise that, and I'm gonna go ahead and take the integration of it from the position on 1, and this is y1 and y2. Okay, so the actual work by trying to raising the other weights would be equal to minus w y over y1 y2. So in this case, minus w, the weight, times the y2. I think I can be able to do that. You have to watch. Okay, y1 in this case. Okay, so u12 is going to be w times y2 minus y1. So this is the amount of the work done by the external force. In this case, the weight of the unit. Okay. Now, what about the U1 to 2? What about for spring? Okay. Here is my spring. Okay. And I'm going to stretch that out. This is a position 1. That's going to be position 2. Now, somewhere over here, when I saw the spring extends. So that means the constantly the force, spring force, is applied to the left, putting the resistance to it. Okay, when I move, the spring stretching to the right, and the spring is applying the opposite direction. I mean opposite forces, which is going to be K times X. K is spring constants. X is the amount of the spring deflections. Okay, and direction here would be a dr, in this case in the x directions. So as you can see that this guy also has a 180 degree. So u goes 1 to 2 in this case, okay, is equal to force times dr. In this case, force is kx, and dr in this case is dx, and the cosine term is cosine 180. So therefore, it's going to be kx dx. It's going to have a minus there. And I'm going to take the integrate between 1 and 2. So this is going to be u goes from 1 and 2. It's equal to minus kx squared divided by 2. This would be position at the 2 and position at 1. And if you integrate them, it's going to be kx2 2 plus kx1 squared divided by 2. So this is the amount of the work done by the force on the spring. All right. So going back to our equation of the energy, T2 minus T1, and I wanted to put that as a T1 and collecting all the positive terms right there. Now, if the mass, now we only talks about the U12 for the, the weights moving upward or downward. And also if the spring is present, so we know what that looks like. And that there might be some force and these forces are not depends on the path. Okay? These are only depends on the end points. It doesn't really matter what happens between x1 and x2. Same thing for moving upward. Okay, the position of 1 and 2. It doesn't matter what happens to the y at the 1.5 or 1.7. Okay, I don't care. Okay, just give me the initial and the final, the position or delta position. Then I can be able to tell how much is the work has been done. Okay, so sometimes you have a friction force applied, which depends on the path. Okay, those are called the non-conservative forces. So here is the energy done by non-conservative forces, and this is we call the energy. I mean the work done by conservative forces, such as the weight, moving up and down, or the springs. Okay, so U actually has the two components in general. So U of the work done by conservative force and the work done by the non-conservative force, and two of the main thing is shown right there. So we already derived these equations. So I'm going to punch that back in here. So U12 is equal plus T1 is equal to T2. Okay, here we go. The first one was minus W, Y2 minus Y1. Second one was minus 1/2 times KX 2 square plus 1/2 times K x1 square. Okay, and this is the U of conservative forces. And there gotta be the non-conservative forces it could present plus T1, which is 1/2 times what is it, mv1 square equal to 1/2 times mv2 square. Now I'm gonna collect the terms. For example, this guy is minus wy2 plus wy1. So all the the parameters or the terms related to 2, I'm going to push that to the other side of the equality. So what's left here is, okay, I'm going to write this guy first, UNC 1, 2, and then write this guy WY1 plus this guy 1/2 times KX1 square. And then what's left is 1/2 times MV1 square equal to WY2 plus 1/2 times KX2 square plus 1/2 times 1V2 square. And this is the energy equation. That's all you have to know. Okay. Now, sometimes we don't write the weight times, and sometimes we write this one as mg. Y is vertical distance, height of 1, and this is going to be mgh2. Okay, so you can kind of replace it. So everything in here, okay, and is a, all the prime parameters. Where are you? Okay, how much was, original position? What's the velocity at the station 1? Same thing for, at the station or position 2. And it has the exactly the same format. Okay, what's so difficult not understanding the energy equation? And this, when this guy is 0, which means that I don't have anything built in like a friction, okay, in my, the dynamic system, then you drop this, and this is the, the only equation that you need to work with. If there is no spring, then you drop this. How simple that is, right? So we're gonna utilize this energy equations for next, few classes, and that's that's about it. Okay, so let's go to here. What time is it? 9:40. I don't think that I can be able to finish anything at this point. Maybe I will stop here. If you have any questions, now is a good time to do that. Let me see. Somebody. Oh, okay. Any questions so far? You guys good?
So far, so good.
Okay. Once again, I try to make the lecture, simple as possible and concise as possible, and give you the direct line of approach, which I believe, but you may have a different perspective because I'm not you. Okay. So you can probably say, oh, it's easy. Yeah. I have moments. It's good, right? But if you do not practice enough, and you're gonna have a heart attack when you get to test. Okay. And I don't really care about the quizzes. Okay. That's why I give, good grades on everyone who tries. Okay. But test is different. And I go down to the, to the third level. So, any points, if I don't see something right, then, unfortunately, there will be a significant deductions. So in order not to be victimized at, I suggest that you take a look at some of the problems in the back of your chapters, and it will definitely help you, in preparations of the test. Okay, that's all I can say. I just wanted to encourage that and emphasize that point. All right. Hey, if you don't have anything else, I hope you have a good night, and we will see you on next Monday.
Professor, I have a question.
Yeah, sure.
Do you want us to show units and like intermediate steps, or just the final result?
No, you do not have to do that until, at the last minute. Okay.
Okay, got it. Thank you.
When you're okay. Okay. All right. but it's preferred if you can show it. But if you have too many steps, like the ones that I show you, right, extra steps here, and those carrying out the unit can be cumbersome. So you can probably put that in the very end, or whenever you feel that you need it, you can do it.
Okay, got it.
Okay. Anything else, guys? Okay. If you don't have it, then hey, have a great night, and we'll see you next week. Thank you and goodbye.
Have a great weekend, Dr. Kim.
Thank you, Professor.
Thank you, Professor.
Professor, see you next week.
Okay. Thank you all. Bye bye.